So we have a wheel with a radius, and it has 3 masses on the perimeter. So mass little m, big M, and 2 big M. They're mounted on the rim of the wheel as shown. So if M is 2 kilograms, so this will make it easier for you. Let's just take this M right here. M is 2 kilograms, so we'll just label it what it is. That's 2 kilograms. So what would 2 big M be? 4 kilograms. Okay, so that guy's 2 kilograms. This guy right here is 4 kilograms. And then little m is what we're looking for. We're trying to find out what is that mass for the wheel to not rotate. Okay, so it's a bicycle wheel, like held up vertically. The axis is right here in the middle. So this wheel is free to rotate. It could rotate clockwise or counterclockwise, but with these 3 masses on the perimeter, the wheel stays put, and we need to figure out what is this mass, this little m, right here, so that the wheel doesn't move. Okay, so we start out by labeling the forces. It's like a free body diagram. So over here we have mg down for that guy. You know, the force of gravity is always straight down. Let's just use gravity as 10. So this is mg, but if gravity's 10 and our mass right there is 4, this mg would just be 40. Okay, and then over here we have mg down like that for the 2 kilogram mass. So 2 times 10 is 20. So we got 20 newtons there. And then this guy, we don't know what it is, so let's just label him little mg, and we're solving for little m. Okay, the axis is in the middle. And by the way, there has to be a force holding everything up. There's got to be some force holding all of this up, but that force is not going to matter, because why? Because it's directly on the axis and therefore causes no torque. So let's just take him off. Okay, he's there, but he's not going to be a part of the problem because he has there's no torque. All right, so this force right here, clockwise or counterclockwise?
Clockwise.
Clockwise. The 20 Newton right there, counterclockwise.
Wow.
And then this mg here, counterclockwise. Okay, so I'm going to erase the problem. Okay, so what we're going to do is we're going to sum the torques. Now the torque equation is force times lever arm, where these two have to be perpendicular to each other. So let's start with our positive. Let's say clockwise is plus, counterclockwise is minus. All right, so let's start over here with this 40 Newton force. Now what's going to be the lever arm for this force from the axis? From the axis over to that force is how far? R. It's the radius. Okay, so here's what this looks like. We're going to go 40 newtons times R. Are these guys perpendicular to each other? The 40 Newton force is perpendicular to the radius. They're perpendicular, which they have to be when you're doing torque. All right, now let's go over here to our negative torques. Let's start with this little mg right here, which we're trying to find little m. Okay, so we're going to go minus. Now, dude, why am I making a minus? Because he's counterclockwise. So this, we're just going to put in mg, that's what the force is. And then what's the distance for that force? What's the distance from the axis over to little mg? R. And is it perpendicular? Yep. So that's R. Okay. Now, for the tricky part of the problem, this 20 Newton force, okay, it's minus because it's counterclockwise. So minus 20 newtons, that's the force. Now, what is the distance for that 20 Newton force? Is it going to be R? Well, look at from the axis up to the force like that. Is R perpendicular to the force going that way? No. But check out what we can do. If you look at this, so when you're doing torque, the distance is always measured from the axis. What is the perpendicular distance from the axis to the force? It's this distance right here. Here, let me put that in a different color. I'll put this in red so you can see it. It's this distance right here, that red line there. Now, what's that red line going to be equal to? We have to do a little bit of trig. What do you think?
I think it's that red line is half the radius.
Uh-huh. Because you're going to go cosine 60 times r. That's what that's equal to. So let me show you how I got that. If you look at cosine 60. So we're focusing on this triangle right in here. So cosine 60 equals adjacent, which is our lever arm, and then the hypotenuse is r. So r is cosine 60 times the radius. And then cosine 60 is 0.5. So our lever arm for the 20 Newton force is 0.5 r. That's the trickiest part of this wheel problem. So this is 0.5 r. Now, in this class, the torques will always cancel. So this is going to cancel to 0. The torques have to cancel if the wheel's not rotating. If the torques didn't cancel, the wheel would be not just rotating, but accelerating, spinning faster, faster, faster. Okay, now what drops out of this problem? What can we cancel in this equation? The r. R is in every part, and then we're going to plug in gravity is 10, right? So what we have is 40 minus 10m minus 10, right? 20 times 0.5 is 10 equals 0. So this is basically 10m equals 30. So m must be 3, which is the answer. So what's the trickiest part of this problem? The thing that made this problem tricky was which part? Finding the lever arm for this 20 Newton force. Finding the distance that was perpendicular to it.